our next speaker is Katharina Schuh. Over to you.
Okay. Yeah, thanks for the introduction. So unfortunately, I cannot join in person, so I have to give, unfortunately, the talk online, but I will talk today about the convergence behavior of the so-called kinetic Langevin samplers in a very specific setup in the so-called, or for so-called non-convex potentials. So yeah, let's start with, apparently my mouse is not working. No, so I can go through it. Okay, so what I'm interested in is, as we have seen already several times, yesterday and today, we are interested in sampling a certain probability distribution, and here it should be of the form that it's proportional to the exponential to minus some potential u, and this potential u can be non-convex. So what I have in mind is what you can see in the two pictures below. Can you see my mouse actually, so that I can?
No, I don't think so.
Okay. So yes, you can see there, it could be some multi-val potential or some banana-shaped potential, as you can see here. And I'm working here in some space RD, and you know probably better than I do, there are a lot of applications for this. And I want to sample these two probability, this type of probability measures by using the so-called kinetic Langevin samplers. They rely actually on the so-called Langevin dynamics we will see in a minute. And here I will focus on the Euler discretization of the Langevin dynamics and on two splitting schemes, the BU and the UBU splitting scheme. And these three schemes we want to analyze. We want to analyze how well what is their convergence behavior of these discretization schemes. And actually we'll see that they will be unexact, so they will only approximately sample our measure, or they will sample a measure with a certain error. And so then the next step, we have also to understand the error they are producing, and so this will be done then in the complexity analysis, and hopefully at the end we will also talk about some particle models. So that's the plan for today. So let's start with the kinetic Langevin sampler and start here first with the continuous dynamics. And therefore we look at the Langevin dynamics. Sometimes it's also called second order Langevin or underdamped Langevin, but actually I prefer to just call it Langevin dynamic. And so here, this is the process XTVT is just a solution of this SDE, where the change in position is just given by the velocity, and then the change in velocity is given by minus the gradient of u and minus gamma vt plus square root of 2 gamma dBt. And so we see that kind of like the first part is something like the Hamiltonian dynamics, and then we have a second part, which is something is an Ornstein-Uhlenbeck process. And so if you look at, for example, some trajectory of this dynamics, here I took u just to be some quadratic potential, then you see really that only noise comes in the velocity component. So it's this path, or this trajectory is rough in the velocity component, which actually makes it harder to analyze later on. And also for the discretization schemes. And so why do we look at these dynamics? So the nice thing of these dynamics is that it has a unique invariant probability measure, the Boltzmann-Gibbs distribution. And here you see already for this Boltzmann-Gibbs distribution that in the X marginal, we directly have our target measure mu we want to sample from. And here for example, for a double well potential, so non-convex potential, you can see like the level set of this Boltzmann-Gibbs distribution. And so, therefore it's, we are interested in the Langevin dynamics, since we have here this nice property that it has the right, that in the X marginal we observe the right potential, the right probability measure or target measure. And so now we want to look at numerical discretization schemes, and the perhaps easiest one is to look at the explicit Euler discretization of this scheme. So if we have, for example, a position xk and vk at a certain point, and we take as a discretization parameter h. Then the next position and next velocity is just updated by this following rule. So taking the old position plus h times the old velocity gives then the new position, and similarly for the velocity component. And here the Brownian motion part is given by taking a sequence of independent normally distributed random variables. And yeah, as I said, this is an explicit scheme, and in particular, this observed chain, or this chain we observe is a Markov chain we can now use to sample then our a probability measure, and we will see later on it's a probability measure which is close to our true target measure. And this scheme has now a local error of order 3.5 and a global strong error of order 1. And so this is one possible scheme, but we can actually look also at different schemes. And these are the following. These are maybe, yeah, I will introduce in the following. So we can also look at the whole SD and split it in different blocks. So we look here at some splitting schemes. And so one famous, or one, I think, which was introduced which was introduced at some point, is this following scheme where we kind of like split it in these 3 parts. And here you see already the Ornstein-Uhlenbeck part I mentioned earlier. And then this Hamiltonian, this part from the Hamiltonian dynamics is split now in a B and an A part. And the nice thing is here that all of the parts can be integrated exactly over a time interval. So, and then the idea is to kind of like combine then these, so combine these different parts together. So the idea is that if we have a discretization step H again, then a possible integrator would be kind of like doing first a step B of size h/2, then a step A of size h/2, then a step O of size h, and then A and B again of size h/2. Or ordering it in a different way. And so with this, we get some splitting schemes, and this and Kleinkühler and Matthews, they have observed that these have weak order 2, but only strong order 1. And let me also mention that for this also was analyzed already in a non-convex setting by Martin Schuh and Guillermo Manchet. I think they are also both in the audience, if I saw it correctly on the list. And so actually we will later on, for the UBU scheme and the BU scheme I will introduce next, we will use some of their ideas of their work. But actually we can also look at schemes with a better order, a strong order, and these are will be the UBU and will be the UBU scheme. And here the idea is that we will split our SD and into different blocks. So we still keep our B block, but now we combine our A and O block to this U block, and this can still be integrated exactly over a time interval. And then as for the Baobab or Obabo or the other names, we can also kind of like integrate it step by step, these different blocks. And this scheme, or the UBU scheme, will have then strong order 2, and we only have one gradient evaluation still per step. And so let me now introduce how these schemes now look precisely. So if we have now our B and our U block, then our B block, well, this can be implemented rather easily. While for the U block, you don't have to remember this formula. It looks very ugly, and I also have to look it up again and again, but I want just to mention, so if I have the discretization step H and I would start in a position X and the velocity V, then my new velocity would be of this form, and my new position would be of that form, and my new velocity of this form. And here the interesting thing is that in comparison to the Euler scheme, where we had just one random variable per step, we take here now 2 independent standard normal random variables, but they are kind of like combined in such a way that they amount later on to the right amount of noise we need to mimic or to to have for the discretization of the Brownian motion part in the SDE. And so this we have to keep in mind for later on, that we have here like 2 standard normal random variables, but otherwise you don't have to remember these formulas. But there is a formula, an explicit formula, and it can be integrated exactly for these 2 schemes. And yeah, then how we get then our Markov chain from this. So yeah, as before for the similar as for the Euler scheme. So we start with a position and velocity at a certain point. Then we take, we have our discretization parameter h and our sequence of independent standard normal random variables. And then for the BU scheme, okay, we first do a U step and then a B step. And similarly for the UBU scheme, we have now actually already 4 random variables in 1 step. And yeah, we took first an h over 2 step, an h step, and then an h over 2 step. And yeah, having now introduced these schemes, I want now to fix the setting where I'm interested in. So which kind of probability measures I will look at. Because I said I will, I'm interested in potentials which are not strongly convex, but still we have some properties on our potential U, and in particular we assume that the gradient of U is Lipschitz continuous, and then I assume as well that the potential U is now only strongly convex outside the Euclidean ball. That means this in particular includes these double well potentials, provided now our potential is then at some point strongly convex, and this is represented in this formula here. So provided now our x and y are the distance of x and y is larger than a particular radius r, then we still this strongly convexity property should hold true. And yeah, this is just the Lipschitz continuity property. And here what I will do next is that I can represent this condition now also in a different way. Namely, this is equivalent to assume that there exists a symmetric positive definite matrix K with smallest eigenvalue kappa and function G, just that I can now split my potential U in a quadratic way and in a, somehow I call it perturbation. And this K, well, this can, a very simple choice for this K would just be to take kappa times the identity, but we can also take another positive matrix K. And for this perturbation G, I want now that this is only convex outside a Euclidean ball with this radius R, represented here in this formula. And one observation is that, well, also this perturbation should also be Lipschitz continuous. And one observation is that I can lower upper bound this Lipschitz constant of the gradient of U by Lk plus Lg, which will occur both later on in the results. Yeah, this is the setup. As I said, this includes in particular these multi-well potentials, provided now the potential is then strongly convex outside the Euclidean ball. Okay, and now having set up what is our scheme, or sorry, what is our sampling method and what is our framework we are interested, or measures we are interested in, now we can come to the analysis for these schemes. So how well do they actually sample this given target measure? And so here we will analyze this using the Wasserstein distance and using couplings. So just a short recap for those who haven't worked for a longer time with couplings. Yeah, just a coupling between two probability measures on some space RD. Well, this is just a probability measure on the space RD times RD, such that this probability measure G has marginals mu and nu. And then the Wasserstein distance with respect to some distance rho. So it doesn't need to be the Euclidean distance. And here I look at the Wasserstein 1 distance. This is just given as the infimum over all possible couplings between mu and nu of the integral of this distance rho, and the integral with respect to this probability measure omega. Yeah, this is the distance we are interested in. And then I said we will use now the coupling method as well to analyze this long-time behavior. And here the idea is that we will look at a coupling step of discretization methods. And here for the Euler discretization, we would start with two initial conditions. So we have like x v and x prime v prime. And then we want to get to the next position and velocity of these two copies. And this is done by that we take here now a pair of random variables psi and psi prime. Thus, they are both now defined on a common probability space such that they both are normally distributed. Sorry, this should be not equal, but no, sorry, this should be equal. So they are both normally distributed random variables. And phi here is just the representation of the Euler discretization. So here, this is just how we get the update from one step. And so kind of like here, in the coupling transition step, this new step we obtain by coupling them through this pair of random variables. But before I come actually to the discretized scheme, we will have a look at the continuous scheme, because there the ideas or the method how we got their contraction it will influence our also how we do it in the discretized setting. Just to mention, so to find now or to get now results on the long time behavior or get guarantees that we kind of like converge to the right or that we converge to some probability measure. Here the idea is that we will try to find a good distance rho here in our Wasserstein distance and an appropriate coupling such that if we start with two initial conditions, that we see that after one step we will come closer, so that we need to find here the right psi and psi prime or how they are connected to each other. And as I said, we will first start now with the continuous dynamics, because there we can kind of learn a bit how the coupling is constructed there. And this we will then kind of adapt then to the discretized scheme. And so in the continuous scheme, there you don't have these kind of like coupling steps, but here there's the idea is that you kind of like you have your Brownian motion, and then you couple your two copies through the two Brownian motions. And for the continuous dynamics, if you start, for example, in the two probability measures mu zero, and we denote mu t and mu t, the law of the two processes or the two copies of the continuous dynamics, then provided we are in the previous set of assumption, which was the setting that we are strongly convex outside the Euclidean ball in Lipschitz continuous, then provided that our Ornstein-Uhlenbeck part of the continuous dynamics is sufficiently large, which is encoded in this condition here, then one can actually find a distance rho such that in Wasserstein 1 distance we get contraction in Wasserstein distance with respect to this rho. And this constant or this contraction C here is a constant which depends on our parameters occurring already in our set of assumptions on gamma, kappa, LG, and this R. And since this actually this distance rho, which I haven't defined here, is equivalent to the Euclidean distance, we also get contraction in Wasserstein 1 distance with respect to the Euclidean distance, paying a price of getting here an additional constant m, which is also dependent on these quantities, but both C and M are independent, for example, of the dimension. And how do we get these to this result? Here the idea was, to construct an appropriate distance function rho and to find the right coupling. And here the idea was that we took a synchronous coupling for large distances. In particular, if we are looking at large distances, this means that either the difference in the position or in the velocity was large. And so if the distance and the velocities was large, one can use the Ornstein-Uhlenbeck process, the Ornstein-Uhlenbeck process helps to get contractivity. while if the distance in the position was large, we could use the strongly convexity property to get contraction. And then for small distances, a reflection coupling was used. And here for small distances, we could rely on a work, or we could use a work by Guillen, Eberle, and Zimmer, where they constructed a concave distance function and showed there that they got local contraction. And then in the end, one had to combine these two local contraction results in a nice way. So we had to glue these two distances in a nice way to get then overall contraction. Let me just mention, so this is one work on the continuous Langevin dynamics. So there are also other people have worked on this. So Dalalian and Briand-Durand, they analyzed in particular the synchronous coupling a lot. And then I mentioned the work by Guillen, Eberle, and Zimmer. They also analyzed they also already analyzed their non-convex setting, but they had still some dimension dependence in their contraction rate, but still we could use their reflection coupling, or the construction of their reflection coupling and the distance function a lot. And they had still some, so their distance rho was not a distance, but a semi-metric. And then also Guillen, Pierre Lepris and Pierre Montmarché worked on this, and they got also rid of the dimension dependence already in the contraction rate. And let me also just mention, so with this approach, if you look, for example, at a strongly convex potential, in particularly at this quadratic potential, one can write down the contraction rate explicitly, which we obtain. Well, in the other cases, one can also write it explicitly, but they become more complicated. And just here in this situation, it's easy to see how the contraction rate looks like. And in particular, if then gamma is of 2 times square root of kappa, then this contraction rate becomes or reduces to square root of kappa over 4. So this was the continuous setting. So now we want kind of like to transfer this to the discrete setting, so to the Euler scheme, and then also later on to the BU and UBU scheme. So so here we now have to look at how we construct the coupling and also the distance function. And as I said, we start with 2 initial conditions, so xv and x prime v prime. And if we now look at the difference of these 2 position and velocity, and so which is kind of like shown in this picture, so then the idea is that we now split our area, this distance, the area of the distance process, so Z and W, in different areas. And so the idea here is that we also want to kind of like use for large distances a synchronous coupling, where we can kind of like use the influences coming from the Ornschell-Uhrenbeck part or the strongly convexity. And so this can be done indeed. So if we are actually outside of this blue ellipse with the synchronous coupling, we could get local contraction if we take a synchronous coupling. So we first sample psi, and then we set psi prime equal to psi. Then with the distance of the form of this 2-type norm, we can actually get local contraction. And then the other way around, so if we look now for small distances, as for in the continuous setup, we look here now inside this green rectangle. We now do not take directly a reflection coupling, but we take this construction of a coupling here. The idea is that we first sample psi, then we also sample independently from this a uniform distributed random variable u. Define here our B, and here you see that B is depends now on our discretization step, H, but H. And then we set now our psi prime with a maximal probability equal to psi plus beta times Q, where Q is of this form here. And in particular, if Q is 0, then we would be on this dashed line here. And yeah, if Q gets larger, then we kind of like move away from this dashed line. And well, actually, we would like to do this always, but then in this, we would like to do this construction psi plus beta times q always, but then the problem would be that this would, that psi prime would not be standard normally distributed. So we have can do this only with a certain probability, and otherwise we take here a reflection coupling. And yeah, this coupling idea actually was already used in by Burabe, Eberle, and Zimmer in their work on Hamiltonian Monte Carlo. There they had, instead of this H, they had the whole runtime of one HMC step. And then it was also used in the work by Martin Chak and Pierre Montmarché on the Obabo scheme. And yeah, and as a as a distance, we have here now some one type norm, and here this function f is some concave function. And one observation we can make is that actually if q is equal to 0, so if we're on the dashed line, then we have indeed a synchronous coupling again. And if h approaches 0, then we see that with this construction, this coupling approaches as well our reflection coupling we had in the continuous dynamics. Okay, with this coupling construction and distance construction, we can get then also a contraction result, namely under the assumptions A, so that we again in this strongly convex setting outside the Euclidean ball, and let now mu0 and nu0 be probability measures on RD, and mu k the case, the law of the case step of our Euler discretization. Then again, provided now that gamma is sufficiently large, so that kind of like the part from the Ornstein-Uhlenbeck part, so is sufficiently large so that we have sufficiently much noise in our system. And now we have also assumption that h needs to be sufficiently small. Then we can show that we can get contraction in Wasserstein distance with respect to this distance rho. And I just wrote down the distance rho in these two different areas. And I think I forgot to mention that. So far I just said that well, this coupling construction works outside this blue ellipse and inside this green rectangle. What we then do is namely that we kind of like glue these two distances, or these two construction of the distances together, and where we have the transition between the two distances, this is where we have this red deformed rectangle. And so kind of like there's the transition between the two distances and the coupling, two coupling constructions. And yeah, with this distance rho then, which is the gluing between the two local distances, let's say it like this, we can get contraction with a contraction rate c. And this distance is again equivalent to the Euclidean distance, because therefore we get also contraction in Wasserstein one distance with respect to the Euclidean distance, paying here a price of getting an additional constant n. And as I said, well, this is shown by constructing this distance and the coupling, and showing that in each step we have contraction. Let me also mention that for the strongly convex case, this was already done by Lime, Kula, Poulin, and Volley. And with what one can show that if U is actually strongly convex, then we can get also in our case, our constant C here would be of this form here, and provided now if we choose gamma of this form, and if our perturbation part of the potential is sufficiently small, which is needed to kind of like to verify that this condition here is satisfied, then we can get a contraction rate of order square root of kappa. Yeah, and now similar things can be done also now for the BU scheme. Here now the problem is what we have to take care of is that we have now like two random variables we have to couple. So we have xi and theta, and xi prime is constructed as in the Euler scheme, and for theta we just take a synchronous coupling. So this is perhaps not the optimal way, but it's a way where we already get contraction. And then under similar assumptions, so if you're again in this situation of our assumption A, and if our Ornstein-Uhlenbeck part or the noise part is sufficiently large, and we have also a condition on on our discretization parameter h, we can get contraction in Wasserstein one distance with respect to the same distance rho. Here, this contraction rate c differs from the one before by, I think, by a constant, but they are still independent of d and h. And again, the idea is similar, constructing the distance and the coupling and showing that in one step we have contractility. And now if we come to the UBU scheme, there we do it a bit differently, because there we use that we can, if we do now k steps of our UBU scheme, we can split it in a different way. And then we see that we kind of like can split it such that in the middle part, we have k minus 1 BU steps. And then, yeah, the right and left-hand side, either a UH half step or a BUH half step. And so here the idea is that we kind of control these two other steps. In particular, so that that we can show that with this distance rho we have constructed for the contractivity of the BU scheme, that if we start with two initial conditions, that after one step we just increase our distance, or we can kind of like control the increase of the distance by 1 plus h times some constant c1. And for both cases. And then the idea is that we get a contraction result for the UBU scheme by just combining it with the contraction result of the BU scheme. And this can, gives us then this contraction result in Wasserstein one distance, here paying a price of having an additional constant C2, which is of this form here. But still our constant M is independent of D and H, and also our constant C2 can be controlled independently of H. Yeah, and so with this contraction results, or the theoretical contraction results, we also did some numerical simulations. And here I have to say, actually, Peter did the simulations. So we also tested our reflection coupling for the banana-shaped distribution. And here you see it on the left-hand side in the normal scale, on the right-hand side in the log scale. And now for different gammas, we did the reflection coupling. And yeah, you see that for large gamma, the reflection coupling and the synchronous coupling behaved very similar. And then at for gamma equals 1, we saw here a difference, that we saw that the reflection coupling actually behaved better than the synchronous coupling. Okay, so now we have seen that our scheme, that we have some contraction results, that we have some convergence to some probability measure, but this might be not our true target measure we want to sample from. So actually we want to sample now, I denoted here by mu infinity, this as a target measure we want to sample from, but it might be that actually the invariant measure of the discretization scheme mu h infinity is not exactly mu infinity. So we need now to bound the difference between these two measures. And so here we can have some strong accuracy results. So we can actually bound the difference between these two measures by h times square root of d times some constant. Under the previous assumptions we had also already for our Euler discretization. And this is some nice, actually short calculation I want to demonstrate here. So if we start here with the distance between mu infinity and mu h infinity, then we can just, since these are kind of like either invariant measure for the continuous or discretized scheme, we can just add the transition kernel. And then in the next step, we use the triangle inequality and add the term mu infinity PHL in both cases. So the transition L steps of our transition kernel of the Euler discretization scheme. And then for the second term here, we can just use our contraction result we had before. So this gives us then this additional prefactor, and then and the Wasserstein distance is now just the Wasserstein distance between mu infinity and mu h infinity. The second term can now be put on the right-hand side, and we can divide it by this term we observed then on the on the left-hand side, and which gives us this this expression here, and this Wasserstein distance of the measures of the two measures, both starting in mu infinity and now doing either the discretized or the continuous dynamics, we can bound by the expectation of the processes doing either the continuous or the discretized dynamics. And here the distance rho, I now wrote down, I upper bounded it now by this following expression, and this is nothing else but just now bounding this arrow of doing either L steps of the continuous dynamics or of the right length, or or H times L, or running the continuous dynamics for time H times L, or doing L step of the Euler discretization. And this can be bounded by H times square root of D times some constant. And let me shortly mention this L was now chosen such that it's of order L such that L times H is of order 1. And so kind of like we get with this, we get a bound on the strong accuracy, or the bound between these two different invariant measures. And with this, we can get complexity guarantees for the Euler scheme. Under the previous assumptions we had for the Euler scheme, we can actually now, if you look now at the measure after k steps of our, if you look now at the distance between the measure of after k step of the Euler scheme and the invariant, the true target measure, we can do again some triangle inequality, adding here a mu h infinity. And then these two terms on the right-hand side can now be controlled by using either the contraction result or the strong accuracy result. And we see that now we can bound the term on the left-hand side by some epsilon if we choose h and k in an appropriate way. In particular, if we choose h to be proportional to epsilon over square root of d, and k of proportional to the logarithm of this Wasserstein distance divided by epsilon divided by c over h. And in particular, that means that if we do in each step one gradient evaluation, then we can give a estimate of how many gradient evaluations we need to do to obtain an epsilon accuracy. And this is just of order square root d over epsilon. The same we can do actually now also with the BU and the UBU scheme. Here I only wrote it down now for the UBU scheme. Similarly, we can bound the distance between the measure new k, so after k steps, and the true target measures by just adding here, doing here this triangle inequality, and then doing for both steps, both sides using the strong accuracy, using the contraction result, and then also a strong accuracy result. Here for the UBU scheme, we have to have an additional constant C2, just which comes from the contraction result there. And for the strong accuracy result, well, if we do it in a naive way under the previous assumption, then we can bound this distance between the invariant measure of the UBU scheme and the two target measures by h times square root of d times some constant. But if we assume now more regularity on our potential u, so in particular if we assume that it's 3 times differentiable and has a strongly Hessian Lipschitz, and is a strongly Hessian Lipschitz, then we can actually bound this difference between these two measures by h squared times square root of d. And so therefore, if we then make the analysis of how many steps or how many gradient evaluations we need to get an epsilon accuracy in the Wasserstein 1 distance, well, with this we get, well, first of all, we get that we have to choose h proportional to a square root of epsilon over d to the 1/4. And with this, if we want to get an estimate on the number of gradient evaluation, this is then of order d to the power 1/4 divided by square root of epsilon. Okay, so here with this, we have now some guarantees of how long we need to run our dynamics, both the Euler scheme and the UBU scheme, to get up to a certain epsilon accuracy. What I want to show you next is I want to look at two other target measures, or two specific target measures. In particular, I will here look now at the particle model. So I will look at a high-dimensional measure and analyze this there, and also on a measure which is still on RD, but which satisfies a very specific equation. Let me perhaps start with the particle model on the right-hand side. So here we are now in RD d times n. So, and here we have now a very specific potential U. So in particular, we have now n particles, all of dimension d, such that we have in the potential U, we want that they have some kind of like confining potential, which later on will satisfy the assumptions we had previously on our potential U. And we have some pairwise interaction between these particles, which is encoded in this potential W. And then on the right-hand side, we will look at a measure on, as I said, on RD, which satisfies this condition here. And here in our potential U, we have that it depends directly, it depends itself on this measure mu. And so we have also, you can see it as having again, some confining part and having here some interaction part, but here's not the interaction between particles, but it's the interaction, between this process itself and it's the measure of the process itself. And so for these two target measures, we can again look at use the Langevin dynamics, the continuous one, either the so-called nonlinear Langevin dynamics, or sometimes it's also called McKean-Vlasov diffusion, but here it's now of second order. So where we have now, instead of U, we have this potential U, depending also on the law of the process at time t. And on the right-hand side, we have here the mean field particle Langevin dynamics. So we have like for n particles, we have, each particle has now, we have the Langevin dynamics here with the potential Un. And for these two situations, or these two Langevin dynamics, one can actually show that we can bound the distance between the law of these two Langevin dynamics, namely provided again that gamma is sufficiently large that our potential V satisfies now our previous assumptions we had for our potential U, which was that it's strongly convex outside the Euclidean ball and Lipschitz has Lipschitz gradients. And then moreover, we want that W, so this interaction part is also Lipschitz continuous, but here the Lipschitz constant has to be quite restrictive in comparison to the other quantities. So in comparison to actually not K, but kappa, gamma, and R. And then if we now look at the law of n independent copies of our nonlinear dynamics and this particle system with n particles, then we can see that we can bound this law uniformly in time by n to the -1/2 times some constant. Or we can also look at the invariant measures, the measures we want to sample from. And there we can also bound this by n to the -1/2 times some constant b. And so this is important now if we want now to sample these two measures, mu n and mu star. Namely, we can also do this now by the Euler discretization, or also then by the UBU scheme. And so if we now look at the law of, now if we run the Euler discretization of the particle system with n particles and want to compare it to the law mu infinity n, so the target measure, then we can do this. Again, we can split it up using here triangle inequality, adding here the mu infinity h n, which is the invariant measure of the particle model. And then we can kind of like, also for this particle model, we can find a contraction result. Here, let me just mention, I think I forgot to mention it so far. So this distance here, rho n, will consist of kind of like taking the distance of all the particles, here the distance rho, summing it up and dividing it by n. And then also for the second term here, on the right-hand side, we can find a strong accuracy result, which is now with this distance rho n independent of the number of particles. And then we can also look at, if you want to sample this measure mu star, but here we take now n copies, independent copies of mu star. Then we can also bound this distance of the n particle system, the Euler discretization of the n particle system, and this measure mu star by doing a similar trick. So adding here also like twice the triangle inequality, so which is we added here also this mu infinity n. And the first two terms are as in the previous calculation. And for the last term, we can now use the result from the previous slide that we can bound the difference of these two measures by n to the -1/2 times b. And that in particular, these first two terms are independent of the number of particles, so independent of n. And so we can also get, with this, we can get guarantees. So if you want to ensure that the term on the left-hand side is bounded by some small epsilon, then we can kind of like get guarantees of how to choose our number of steps, small k, how to choose h, and how to choose then the number of particles n. And also for the UBU scheme, we can do this analogously, but here again, if we assume more regularity now on both on V and W, then we can improve actually the second term here by having here now instead of h squared and then a different constant. Yeah, and so with this, I want to already come to an end. So we have now seen that we have now seen three kinetic Langevin samplers, and we have seen theoretical guarantees on the long-time behavior. So we have seen contraction results for all three of them in Wasserstein 1 distance. Then in the next step, since these schemes, they do not sample our true target measures, but we have always some bias. We also analyzed the error we are making. So we have shown also some complexity guarantees for these schemes. And then in the end, we also looked at some specific high-dimensional setup and also on this specific nonlinear measure. I think I forgot actually to mention that this has actually then applications in, I think, in deep learning. If you want to train some neural networks there, this type of measure, for example, can occur. And yeah, we have also seen then, or we have applied results for this type of measures. And with this, I want to come to an end. The results mainly relied on these two works and also the other works I mentioned through the talk are cited here, but let me just mention there, of course, are many more works. I just cited the kind of like most related works. I used the most related results of the works I used in the presentation. But yeah, thanks for your attention.
Okay, do we have any questions for Katharina? Time for one or two. Yes.
Can you hear me?
Yes.
For the UBU scheme, I think if you take gamma to be 0, it reduces to basically the splitting scheme for the Hamiltonian part. One of the splitting schemes. And if you do the asymptotic bias analysis for that, everything follows through, I think. So my question is, for the UBU, you had some better dimension dependence. Because you have high regularity, can you do that for the usual splitting schemes under high regularity to get better dimension dependence?
So I'm not sure whether I understood your question correctly. So you want to take gamma first to 0 so that you don't have any noise in your system anymore?
Yes.
Okay, but then you actually might run already in troubles because then you would just do the Hamiltonian dynamics.
Yeah,
and so,
okay. But the contraction will still hold for Ubabo or Baoab. But then you just do for the asymptotic bias part. You don't need contraction. It's just two separate parts of proof. So, but then for the asymptotic bias analysis, I think you can just take gamma to be 0 first. Run through all of what you're doing to get this higher under this high regularity, you get better dimension dependence, and then you add on the OU part, which is exact, and it will not give you it won't add on any extra dependence in particular. So I'm just curious. I don't see a part where under this high regularity condition, where you get independent dimension dependence, your UVU scheme gets this, but the Baobab or the Babaru doesn't.
So, to be honest, I would need to have a closer look to the Obabu scheme where this difference is in. But so therefore, I'm not sure whether I can say anything where there is the difference currently. It's just like yeah. Therefore, I cannot actually say where the difference is between this. Where in the calculations there might be where you lose then this one order and the strong order for the Obabu scheme. I think that's the question. Why, if I understood it correctly, that why you lose one strong order in Obabu in comparison to UVU?
Really strong order. In the asymptotic bias analysis, you don't. You can just split essentially between the OU part and OU part.
Yeah, I would need to have a closer look to the Obabu scheme, to be honest. I can, yeah, I'm not that familiar with how the analysis is done.